So what exactly is a covalent bond? Well, a covalent bond is the result of two nuclei sharing electrons. And the whole goal of this, can we go back to what we talked about with ionic bonding? The whole goal of this is to satisfy the number of outer shell electrons that make it the most stable. We go back to that octet rule. Most of the time this is 8, sometimes it is 2. So if I take a look at two hydrogen atoms that are here, hydrogen wants to satisfy what's called the duet rule, which is a little bit different than the octet rule. That is, hydrogen wants to have 2 electrons in its outer shell, not 8. Well, if one hydrogen donated an electron to another, one of the hydrogens would have 2, but the other would have 0. So one would have the duet rule satisfied, but the other would not. So what ends up happening is that one hydrogen atom shares its electron with the other, and vice versa. The other hydrogen shares it with the original hydrogen. Things share in pairs. So what you end up with is a shared pair of electrons that exist between the two hydrogens. This results in the duet rule being satisfied for both hydrogens because both hydrogens claim both of those electrons because they're shared in between them. And this results in a chemical bond that is being formed, a covalent bond, and you end up with a hydrogen molecule, which you see there as H2. So really it's these types of strategies, this type of sharing of electrons between different atoms that are going to result in these covalent bonds being formed. So as I mentioned before, it's a little bit different than ionic bonding, but hopefully as you see the sharing of electrons over the course of time, you'll understand how this idea works. So the concept of the Lewis structure. Lewis structures are designed to help us visually show the electron sharing associated with covalent bonding. It shows the number of electrons that are shared, it shows how those electrons are being shared, and it plays a really huge role in determining how many electrons are shared in between different chemicals and how those bonds are being formed. I know I've said it multiple times, but I'm trying to get the point across here. So let's consider fluorine. Fluorine has 7 valence electrons in its outer shell, and it only needs 1 valence electron to satisfy the octet rule. And then let's consider hydrogen. Hydrogen has only 1 valence electron and only needs 1 for a full outer shell, so the donation of electrons between one and the other doesn't really make a whole lot of sense. Hydrogen, if it donated its electron to fluorine, would result in fluorine having a full outer shell, but hydrogen having no valence electrons. If fluorine were to donate its electron to hydrogen, hydrogen would have a full outer shell because it would have 2 valence electrons, but the fluorine would only have 6. So it doesn't make much sense to donate electrons in this situation because there really isn't a way where all of the duet and octet rules have the ability to be satisfied. So what we do is we share, and you can see this between a variety of different atoms on the right-hand side here. Hydrogen and fluorine are going to share a pair of electrons. So you see the electrons that exist between the H and the F, once the sharing has occurred, those are a shared pair of electrons that represent a covalent bond. You could say the same for fluorine and fluorine. And bromine and fluorine, each of those atoms has 7 valence electrons in its outer shell. So a donation of electrons from one to another really doesn't make a whole lot of sense in regards to satisfying the octet rule for both atoms. However, if each one shared an electron with each other, well, then what you end up with is a shared pair of electrons between them. The octet rule satisfied for both fluorines, or bromine and fluorine if you look at the bottom pair. And thus, you have a covalent bond that forms in between them. So it really depends on the situation, and it will also depend on the situation on how many electrons are shared. And we'll talk more about multiple covalent bonds here in just a moment. But as you see, the shared pair of electrons are known as bonding electrons. And I know previously it showed them as a pair of dots that were in between the two atoms that were present. And some books, some people will show it that way, but I don't like that. I really like to be able to differentiate between the individual electrons that are on the outside of the atom. We'll talk about lone electrons in just a moment, but also to differentiate them between the shared electrons. The line in the middle represents a shared pair of electrons, so I ask that you please show these as lines. I hate the shared dot pictures. I get the point to show the shared pair, but it's frustrating. There are better ways to do this. Seriously, please just draw a line. Okay, please just draw the line. It will make your life easier. It will make my life easier. It will make me happy. It will make other professors happy. I don't care what they say. My way is the right way, and you can fight me about that. Anyways, Non-bonding electrons are pairs of valence electrons that are not involved in the electron sharing process. So these are what are referred to, sometimes they're referred to as lone pair electrons. I'll probably refer to them more often as lone pair electrons because that's just what I'm familiar with. But if we look at each of the following structures, we can see that the dots that are not in between the two atoms, or dots that are not in a line rather, are considered to be lone pair or non-bonding electrons. So if we take a moment, let's think about how many do we see in each of the following structures. On the left molecule here, the H2, we have a pair of bonding electrons, but no non-bonding or lone electrons. In HF, we have a pair of bonding electrons between the H and the F, and we have 6 non-bonding electrons located on the fluorine. Between F and Br and F, we have a pair of bonding electrons each, but each has a total of 12 non-bonding electrons on the outside of it. So fairly easy to go through and count those. But again, just as always, practice, practice, practice. Now, as we mentioned before, covalent bonding can involve the sharing of electrons, but it can involve the sharing of more than one pair of electrons, and we refer to these types of bonds as either single, double, or triple bonded. Single bonds involve the sharing of a single pair of electrons. Double bonds involve the sharing of 2 pairs of electrons, and triple bonds involve the sharing of 3 pairs of electrons. Now, determining whether it shares 1, 2, or 3 pairs is dependent upon a couple of different factors. It depends on what atoms you're looking at. It depends on how many electrons need to be shared in order to satisfy the octet rule. So there's quite a few things that we need to consider before we go through and try to determine how many electrons are being shared. We'll talk about that process in a moment. And explicitly understanding that bonding electrons and non-bonding electrons occurring in pairs is something that's quite important. Now, do we see Lewis structures and compounds that have rogue single electrons available? Yes. In fact, there was actually one of those on the AP exam this past year that threw some of my students for a little bit of a loop, but for the most part, they actually figured it out quite well. But I just ended up with really good kids, and I feel like I do a good job. So, but that being said, this helps us with counting electrons when we look at Lewis structures, because we're going to end up with pairs of electrons. So electrons will occur in even numbers as we go through and do this process. Knowledge of bonding and atoms themselves and the tendencies of how atoms bond helps to eliminate mistakes. So let's consider nitrogen. Nitrogen has 5 valence electrons in its outer shell in its normal state when it exists as just an atom. It needs 3 more to have a full outer shell, so what you end up finding is that nitrogen tends to form 3 bonds, right? If it shares 3 electrons, it gets 3 electrons in return, so as a result, it would end up having 8 electrons in its outer shell. So we find that nitrogen tends to form 3 bonds. We consider oxygen. Oxygen has 6 valence electrons. It needs 2 more to have an outer shell, so it typically forms 2 bonds. And carbon has 4 valence electrons. It needs 4 to have a full outer shell, so it will typically form 4 bonds. So this is known as the NOC rule. NOC means nitrogen, oxygen, and carbon. I'll be perfectly honest with you, the first time I heard this was when I taught at UC. Never heard of that before, but some professors swear by the NOC rule, so more power to them as they go through and help you guys through this. But it does help with tendencies. Is this always the case? Not necessarily. There are many instances in when the NOC rule does not necessarily apply. But again, understanding periodic trends and periodic tendencies does help us to understand how many bonds these things typically will form. So let's do a quick review and quick check. I'll give you a few moments to look over some of these questions here. The first question here, I just want you to know which of the following would you expect to have covalent bonding? Again, think about what we've talked about previously in terms of ionic bonding versus covalent bonding, metals and nonmetals versus all nonmetals. And then I want to know which of the following is inaccurate about the line represented by the molecule HF here. So take a few moments, we'll come back and we will discuss it in just a moment. All right, so looking at the first question here, it says, which of the following would you expect to have covalent bonding? Remember that covalent bonding exists between 2 non-metals. So I would expect HBr to be what is covalently bonded here. And then it also asks which of the following is inaccurate about the line represented. And the first statement there says it represents 2 shared electrons. Well, remember, lines in between atoms represent 2 electrons that are shared between them, which also represents covalent bonds. So A and B are accurate. Representing non-bonding electrons, well, those would be the dots that are on the outside. The line does not represent non-bonding electrons. It represents bonded electrons. So the incorrect answer there is C. It represents non-bonding electrons. I'd also like you to take a moment here and determine the number of bonded electrons and non-bonded electrons in the following Lewis structures and designate the bonds as being either single, double, or triple bonds. So again, look at the number of lines that are present there. Remember that each line represents a pair of electrons, and we will come back and talk about them in just a moment. All right, so if I'm looking at the very first question here, it wants to know how many bonded electrons and non-bonded electrons are here. So let's count them up. So I'm just going to count up the number of lines. So 1, 2, 3, 4, 5. There's 5 lines. 5 lines represents 10 electrons. Remember, each line represents a pair. So there's 10 bonded electrons in that first one, and I see no dots on the outside, so no lone pairs. So there would be no non-bonded electrons. The next one over, I look at HCN, count up the number of bonds, 1, 2, 3, 4. So each bond represents, again, 2 bonded electrons, so multiply by 2, so that's a total of 8 bonded electrons. You have a non-bonded pair on nitrogen, so 2 non-bonded electrons. And then CO2, very similar. I have 1, 2, 3, 4 lines. Each represents a pair of bonded electrons, so that results in 8 bonded electrons. And then I have 8 dots on the outside of both of those oxygens combined, so 8 non-bonded electrons. So very easy. Go through, count the number of lines, multiply by 2, and just count the dots on the outside. That will tell you the number of bonded and non-bonded electrons that are present in each of these individual compounds. Okay. So what I'm going to do now is something a little bit different. I deviate from many textbooks when I go through and draw out Lewis dot structures. And the reason I do it this way is because it eliminates so many exceptions to the rule, I guess would be maybe the best way to describe it. I've come up with a set of rules to help you draw out your Lewis dot structures. And I promise you that if you draw them this way, you follow the steps, you end up being less error prone. You don't make mistakes if you follow these steps. And it's one of the biggest things I can promise you is just this way is going to make your life a whole lot easier. I can 100% promise you that. You just have to follow the steps, work through them. This is something we're going to do together. I'm going to present the steps, and I want you to write them down. I really want you to take in what these steps are, because this is a systematic approach, a very systematic procedural way to draw out your Lewis dot structures and to draw them out correctly. And even if you're in a course that is beyond this, let's say you're in a 1040 course, you're in a general chemistry course, and you have things that go beyond the octet rule, you can still apply these rules to it. There's just a little bit at the end that we end up adding to it. So if you want to see more of that, go check out one of my Chemistry 2 or my AP Chemistry videos, because it walks through a little bit more detail than what I do here. We don't do anything with exceptions to octet rules here in this 1030 course. So that being said, follow these steps and you will draw Lewis structures. Remember, we're drawing Lewis structures for compounds. We've done this for atoms before, but drawing them for compounds is going to require something a little bit different, okay? Step 1, determine the type and number of atoms from the formula. Break down the chemical formula you have, write out the number of atoms and each atom that's present. So if you're looking at a chemical compound with H2O, write out the fact that you have 2 H's and 1 oxygen. Determine the total number of valence electrons. Remember that is information that is based off of the element's location on the periodic table. So if I look at a periodic table, I should be able to determine the number of valence electrons in individual atoms, and then I can step by step determine the total number of valence electrons I need. This essentially tells you roughly how many electrons need to be in your structure when you are done. So step 3 is determine the central atom. This is the atom that is furthest away from fluorine but not hydrogen. Okay? I'll repeat that. Determine the central atom. It is the furthest away from fluorine or not hydrogen, or if you're familiar with the concept of electronegativity, it is the least electronegative atom that is present in the compound that is not hydrogen. If your molecule has just 2 atoms, there really is no central atom, because 2 atoms are just going to bond together. It doesn't tell you how the atoms bond together because it doesn't need to, right? 2 atoms are just going to bond together. Step 4. Bond your other atoms to your central atom with single bonds. So figure out what your central atom is and bond everything. Take one line and put it in between each atom that you're going to surround the central atom with, and draw a line in between those atoms and your central atom. The next step, step 5, is to add pairs of valence electrons or lone electrons or non-bonded electrons, depending upon your nomenclature, to all atoms to reach the octet rule. You may end up going beyond the number of electrons in step 2. That is okay. Okay, I cannot stress that enough. You may end up adding more dots than what you find in step 2. That's fine. We can change that as we work through it. Read step 6. If the number of electrons in the structure is equal to the number of valence electrons, it is done. So if in step number 5, you add up the total number of electrons in the structure and it's the same as what you have in step 2, you're finished. You've drawn the correct structure. If not, you need to remove 2 lone pairs of electrons and create multiple bonds until the number of electrons in your structure and valence electrons is the same. And keep in mind that halogens, that is those things in group 17, fluorine, chlorine, bromine, etc., and hydrogen can only form 1 bond. So there's a set of rules you work through. If you end up building your structure and you have more electrons than are necessary, more electrons than you need in step number 2, what you're going to do is you're going to remove pairs of electrons and add lines in between them. What that does is that reduces the total number of electrons in the structure, but it maintains the octet rule, so you don't have to worry about going back and making sure, oh, everything has 8. This systematic approach, these 6 steps, will work for nearly every single Lewis dot structure that you will draw in this class. I promise you that. So what we're going to do now, and what I'm going to do is I'm going to switch over to my iPad, and I'm going to show you how to apply the steps for each of these 6. It's going to take a little bit of time. It takes a little bit of practice, but as we do this, notice how I follow the individual steps. I'll be back with you in just a moment. All right, so as I mentioned before, all we need to do with each of these is just go through and follow the steps. So we'll do this one step at a time for each of these 6, and then we'll take a look at some more. Just again, it's all about practice with this. If you follow the steps, you'll do just fine. So I'm going to follow the steps. So step number 1 is determine the number of atoms of each. So I have 1 nitrogen and 3 chlorines that are based off of that chemical formula. Next step is to determine the total number of valence electrons that are present. So again, that is periodic table based. If I look at nitrogen on the periodic table, I find that there are 5 valence electrons for each atom of nitrogen. There's 7 for each of chlorine, but there's 3 of them. So that ends up with a total of 21 here. So we're just going to add those together. So I have 26 electrons to play with as I build my Lewis dot structure. So those are the first couple of steps. The next step is determine your central atom. Remember, that is the atom that is furthest away from fluorine. That is not hydrogen, or the least electronegative atom, if you're familiar with that. We'll talk about electronegativity later on. So here, we're going to use nitrogen as our central atom. And I guess it is good to note that your central atom a lot of times is just going to be the first element that is listed in your chemical formula. Not always, but sometimes for the most part it is. Again, just depends on the formula you're looking at here, but we're going to start with nitrogen as our central atom. We're going to connect 3 chlorines to our central atom, and we're going to connect them all with single bonds. All right, now the next step is to add lone pair electrons or valence electrons in order to satisfy the octet rule. So we need to look at the bonds that are connected to each of these and how many electrons they need in order to achieve 8. So if I take a look at, for example, chlorine, this chlorine here has 1 bond that is attached to it. So that means it already has 2 electrons attached. It needs to have 8, so what we're going to do is we're going to add 6 electrons on the outside of it. And what you'll notice is that it is the same for each chlorine that is around the central atom. The same sets of rules apply. So we're going to add 6 dots to make sure that it has a total of 8 electrons in its outer shell. If I look at nitrogen, nitrogen already has 3 bonds that are attached to it, so that's a total of 6. So in order to get 8 electrons, I need to add 2 more lone dots to its structure. So we're going to add 2 dots there on nitrogen. Now what I need to do is I need to add up the total number of electrons and see if it's 26. So I'm going to start with the bottom left chlorine. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there's 26 electrons in my structure. That matches the 26 electrons I had originally. I'm done. That's exactly how you go through and draw that Lewis dot structure. So that is the correct structure for NCl3. Let's continue moving on. We're going to scroll down here. Let's do pH3. And again, we're going to follow the exact same steps that we did in our last Lewis dot structure. So first thing here, I have 1 phosphorus and 3 hydrogens. Phosphorus provides me with 5 valence electrons. Again, that's periodic table location based. Each hydrogen is 1, so that's 3. So I have a total of 8 valence electrons to play with here. Phosphorus will be my central atom. Again, it is the furthest away from fluorine. That is not hydrogen. Can't be hydrogen, so it has to be phosphorus here. We're going to attach each hydrogen with a single bond. All right, now remember, when we do this, the next step is to add lone pairs to satisfy the octet rule. Remember that hydrogen is different. Hydrogen only wants 2 electrons in its outermost shell. So for each hydrogen that's here, a bond is already attached. Remember that a bond represents 2 valence electrons. So the octet rules are already satisfied for all of the hydrogens. If I look at phosphorus, phosphorus wants to have 8. If I look at the structure here, it already has 6 electrons attached. In order to have 8, we need to add 2 in order to make that happen. Okay? The numbers that are here, and I should bring this up as well. The numbers that are here, do not bring those over when you count over the number of valence electrons in the structure, okay? Because the number of valence electrons that are present on each atom can shift within the Lewis structure. So don't always anticipate that it's going to have 5 things attached to it. You have to take into consideration the octet rule. So follow the rules as they are given. Ignore the numbers that I just circled or squared until you go back and recount. So as I do this, I count them up again, 2, 4, 6, 8. I have a total of 8 electrons in my structure. This is done, okay? So again, notice I don't worry about the 5. I don't worry about the 3. I don't think about those things. I just focus solely on the number of valence electrons that are in the structure. I go back and I recount, okay? Let's do one more here. Actually, we'll do a couple more. CCl3F, again, same procedure here. So step 1, we have carbon, we have 3 chlorines, and a fluorine. So 4, 21, and 7. Again, look at your periodic table and figure out how many valence electrons there are based on that periodic table location. Each carbon has 4, each chlorine has 7, times 3 is 21, and fluorine has 7 as well. So when I add these up, 32 electrons to play with in my structure. Carbon will be my central atom as it is furthest away from fluorine, not hydrogen. Attach everything to your central atom. For this, it does not matter where you put the chlorines and fluorines. So the fluorine could be on the right side, I really wouldn't care. All right, so now what we need to do is, again, add lone pair to satisfy the octet rule. Don't worry about these numbers. We're solely focused on how many electrons are in the structure and how many more we need to add to get to the octet rule. Fluorine, again, everything wants 8. Fluorine has 2 attached, so we're going to add 6 dots to get to 8. And it's going to be the same for each chlorine. If you look at carbon, carbon already has 4 bonds attached. 4 bonds implies that there are 8 electrons already attached, so we add nothing to our carbon. And now let's add them up and see what we get. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 in that structure. That is done, and that is a correct Lewis structure. Again, I'm following the exact same set of rules that we just went through and discussed. All right, let's look at a couple of more practice problems here. So HCN. Sorry, somebody's driving by with a very, very large motor. So, good for them. HCN, same steps here. Step 1. So you have an H, C, and an N. 1 valence electron, 4, and 5. For a total of 10 electrons in our structure. We're then going to find our central atom. Our central atom here is carbon. Attach everything with single bonds to your central atom. All right, now we follow the same set of rules. We had lone pair to satisfy the octet rule. Hydrogen here, we don't need to add anything to. It already has 2 electrons. Remember, hydrogen is different, only wants 2 electrons in its outer shell, so it's good. Carbon here has 2 bonds that are attached, meaning that there are 4 electrons already attached. It wants to have 8, so we add 4 dots. And nitrogen here already has 2 attached. It wants 8. We add 6 dots. Remember, when we do this step, we can have more than 10. We'll work its way back down to 10. So don't let this limit the number of dots you add in that next step, okay? Now, count them up. 2, 4, 6, 8, 10, 12, 14. We have 14 in our structure. That's too many. So what we're going to do here is we're going to take away 2 lone pair and put a bond in between where we removed the 2 lone pairs. Since we can only remove them between carbon and nitrogen, we're going to do that. So I'm going to take away that. There we go. And I'm going to add another bond in between them. Sorry, technical difficulties. There we go. So what you'll notice what this does is it keeps the octet rule satisfied. So if I look at the number of electrons that are attached to carbon, 2, 4, 6, 8, and the number attached to nitrogen, 2, 4, 6, 8, octet rule is still satisfied. But what it does is it reduces the total number of electrons in my structure by 2. So now when we recount 2, 4, 6, 8, 10, 12, I have 2 fewer electrons. Now that's still not 10. So we keep doing this process until we have the correct number of electrons in our structure. So I'm going to take away these 2. Take away those 2. Rewrite that. Okay. Struggling here. I'll figure it out one day, folks. Okay. So again, octet rule still satisfied, but now we have 2, 4, 6, 8, 10 in our structure, so it's done. Again, the steps are simple to follow. Okay? It takes a little bit of time to get used to writing these structures and practicing, but over time, you kind of get the idea. It's the same steps every time we do this. Let's do 2 more. CO2, same steps. So carbon, 2 oxygens. Each carbon has 4 valence electrons. Each oxygen is 6 times 2 is 12. So I need 16 electrons in my structure. I make carbon my central atom and single bond everything to my central atom. We now add lone pairs to satisfy the octet rule. Again, octet rule, everything wants to have 8. So we need to make sure that everything has 8 in its outer shell. Each oxygen only has 2 electrons attached, so we're going to add 6 dots. The process is the same for both oxygens. And for carbon, as we see here, we have 4 electrons already attached, so we need to add another 4. So again, we follow that step here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So 20 electrons in my structure is too many. We need 16 in our structure. So follow the rules we just talked about. Take away 2 lone pairs, 1 from each atom, and then add a double bond in between them. So all right, and if we go through and redo that, we find that we have 18 in our structure, still too many. I want you to keep in mind that when you go through this process, molecules like to be symmetrical. And so if we have a choice between where we're removing valence electrons, we want to try to keep this molecule as symmetrical as possible. Just atoms tend to like to be that way. They're more stable, if you will. So we're going to add 2 more, or take away 2 more lone pair. And add another bond here, and so we end up with 16 in our structure. So there you go. All my octet rules are satisfied. We have 16 electrons in our structure. We are good. Let's do one more practice problem, and then we will move on. Last one here we're looking at is water. Follow the same steps. So 2 hydrogens and an oxygen. So 2 valence electrons, 1 for each hydrogen, and 6. So for a total of 8. Follow the same steps we did before. Oxygen will be our central atom. We're going to attach hydrogens to them. Remember that hydrogens follow the duet rule. They only want 2 electrons in their outer shell, so by having a bond attached to them, they're already good. Oxygen, however, because it has 2 bonds attached, has 4 electrons on it, it wants to have 8. Add 2 more lone pair. So 2, 4, 6, 8. And our structure is now complete. So what you'll find is that it just repeats itself. Follow those steps. It is a very formulaic process. The more you practice with it, the better you get with it, okay? Few more practice problems coming up. We're going to mix in the ionic and covalent Lewis dot structures that we've talked about. And then once we've done that, we'll continue to move forward. But this is one of the most fundamental processes you're going to learn in here because this builds on itself. Doing this correctly leads to correct geometries, which leads to correct polarities, which leads to correct intermolecular forces. So making sure that we build all of these molecules correctly is super, super important moving forward. I'll bring you back in just a moment. All right, so I just wanted to give you a couple of mixed practice problems as we continue to move forward. So the first one here says potassium iodide. And I know you've been doing Lewis dot structures for covalent compounds, but it is important to be able to differentiate between how you do Lewis dot structures for ionic compounds as well as covalent compounds. Potassium iodide's chemical formula is Ki, meaning that it is a metal plus a nonmetal. And so as a result, we're going to draw our Lewis dot structure a little bit differently. Remember, K has 1 dot in its Lewis dot structure, and iodine has 7. So the transfer of electrons is going to be a little bit different. We are going to be donating electrons versus sharing them. So again, please make sure that you understand there's a difference between how we do ionic compounds, like what we have here, versus covalent compounds. So in this instance, that potassium is going to donate its electron to the iodine, and so our Lewis structure is going to look like this. Okay, so again, that's different than the rules that we set forth previously. Now, this is something that we have talked about in our previous chapter. We've talked about how we go through and draw out Lewis dot structures for ionic compounds. All right, the next one we're going to look at here is CH2O. Again, follow the same set of rules we did previously. This is a covalent compound because we have all nonmetals, so we are going to follow the Lewis dot structures that we discussed previously in this video. So start off with carbon. We have 2 hydrogens and an oxygen. So we have 4 electrons. 2 hydrogens, 1 valence electron each, so that's 2. And each oxygen has 6. So we need a total of 12 electrons in our structure. We're going to start with carbon as our central atom. It is the one that is furthest from fluorine, that is not hydrogen. And we're going to single bond everything to our central atom. Remember, we had lone pairs to satisfy the octet rule. Everything in this molecule wants to have 8 valence electrons except for hydrogen, which wants 2. So each hydrogen is good because it has 1 bond attached. Oxygen has 2 electrons attached because it has a bond attached to it, so we need to add 6 dots. And the carbon here has 3 bonds attached. That's a total of 6 electrons, so we're just going to add 2 here. Count them up and see if we get 12. So 2, 4, 6, 8, 10, 12, 14. So that's too many. So again, just like what we've talked about previously, we take away 2 lone pair. Here we go. Getting better at it. And add another bond. And when you count them up again, you get a total of 12, and our structure is done. So again, just follow those systematic steps as we go through and build our Lewis dot structures. Our last one here on this side is N2. So again, follow the same steps. This is a covalent compound, again, all nonmetals, so we have 2 nitrogens. That's a total of 10 electrons because each nitrogen has 5 valence electrons in its structure. It's just 2 atoms, so there really is no central atom. We just kind of bond it to itself. And again, add lone pair to satisfy the octet rules. Each nitrogen is currently sharing a pair of electrons, so that's 2. Each nitrogen wants to have 8, so we just add 6 dots. And add them up, so 2, 4, 6, 8, 10, 12, 14. So we have too many electrons. So what we do is we just remove pairs and add a bond in between them. Again, that retains the same number of valence, retains the octet rule, but reduces the total number of valence electrons by 2. We recount it up, we get 12. That's still too many, so we're going to have to do this process one more time. There you go. 2, 4, 6, 8, 10. All my octet rules are satisfied. There's a triple bond between those nitrogens. Simple enough. All right. So what we have here is chromium 3 oxide. Okay. So again, a little bit different here. This is an ionic compound. If I go through and do a little bit of nomenclature, I can write out the structure here. So chromium 3, so chromium Cr. Remember that the Roman numeral tells you the charge is 3+. Oxide, oxygen is a 2-, so cross and drop, so that ends up being Cr2O3. So rather than having to go through and show the transfer of electrons, I can actually just write this out as is, because I know that I'm going to have 2 chromiums, each with a 3+ charge, and I know that I'm going to have 3 oxygens, each with a 2- charge, and a full outer shell. Just like that. Again, the difference between ionic and covalent bonding definitely shows when you go through and write out those Lewis dot structures. PF3 and CCl4, the only ones that are left. So PF3, so phosphorus, 3 fluorines. Phosphorus is 5 valence electrons. Fluorine is 7 times 3 is 21. So 26 total valence electrons in your structure. Phosphorus is your central atom. It's the furthest from fluorine because fluorine's your only other option here. We add lone pair to satisfy the octet rules. Again, everything wants 8. Each bond represents a pair. So each fluorine is going to want 6 because it already has 2 electrons attached. And phosphorus wants a single pair because it already has 3 bonds, which is a total of 6 electrons attached. So now what we do is we go through and we count them up and we end up with a total of 26. And we're done. Again, that systematic process, it works so well. You just have to make sure you follow the steps. But notice I'm not deviating from anything that I've done previously. I'm following the exact same steps that I've done previously. 4 valence electrons in carbon, 7 in chlorine, times 4 is 28, so 32 in our structure. Carbon's your central atom. Attach everything to your central atom and add lone pair to satisfy octet rule. Count up, you get 32. I can't make it any easier, guys, okay? So take your time. Practice, get good with it, okay? And then that will help you as we continue to move on with some of the more complicated things. Because remember, as I mentioned before, this unit builds. So knowing how to do this is very essential for us to be able to do other things that we're going to do here in just a moment. So as we continue the process of building Lewis dot diagrams, something we also need to consider are what are known as polyatomic ions. And polyatomic ions are built and designed the exact same way. We follow the exact same steps that we've done previously. Figure out how many valence electrons you have, number of atoms, count them up, get the total number of valence electrons in the structure. Figure out your central atom, Attach everything to your central atom with single bonds, add lone pair to satisfy your octet rules, and then reduce if necessary. The only difference, though, is that we need to take into account the charge of the ion when we count the total number of electrons in the structure. So if we consider something like NO3-, if I were to count up the total number of valence electrons just using the elements that make up NO3-, I end up with a total of 23. And if you remember, we talked about electrons occur in pairs. Well, it doesn't make much sense to have an odd number because electrons occur in pairs. Odd numbers, it's not a pair. So we need to take a look at the charges that are there. A 1- charge indicates an additional electron. So rather than 23, we have 24 electrons in the structure. And then lastly, because it is an ion, very similar to how we do ionic bonding, we put brackets around the ion and put the charge on the outside. So very similar rules apply. The only thing we need to take into consideration is the actual charge of the ion itself. Taking that into consideration, we either add or remove electrons in order to get the correct number of electrons in your structure. So for example, if it were a positive charge indicates that we have fewer electrons. So you're going to subtract an electron or two from the total number that you have here. And it is based off of the numerical value of the charge as well. So something that is a 2- charge, you're going to add 2 electrons to. A 3- charge, you're going to add 3, and so on. So let's go through and do some practice problems with these, and we'll be with you right now. So you can see that these are the polyatomic ions that I want you to draw Lewis dot diagrams for. We'll do them together here in just a moment, but try them and practice and see what you come up with, and we'll be back in a moment. All right, so let's rock these just like we did the other ones. So SO4, 2-, so I'm just gonna leave this kind of in big screen mode here. Hopefully there's plenty of room to write, I guess we'll find out. We have a sulfur, and we have 4 oxygens. Oh, that's much nicer. Yeah, there we go. So we end up with 6 for sulfur, 4 oxygens. Oxygen is 6 as well, so 24. So that is 30. But there's a 2- charge that's here. So we're going to add 2 more electrons to it. So that means that we have 32 in our structure. And now everything else is pretty much just the same. We get our central atom, sulfur. Single bond everything to our central atom. Add lone pairs to satisfy octet rules. So 6 on each oxygen. Sulfur doesn't need anything. And when you count them up, you get a total of 32. The only thing we need to do is put that in brackets and put a charge on the outside. So there you go. Now, if you're taking 1040, this Lewis structure is actually going to look a little bit different, and that has to do with the fact that this Lewis structure actually does violate the octet rule. There's something that is known as formal charge. So if you're interested in that, I do have an AP video that does cover that because it does make this structure look just a little bit different. Okay? So NH4+, so we have nitrogen, 4 hydrogens. So nitrogen is 5 valence electrons, 4 hydrogens is 4, so that's a total of 9. It does have a positive charge here, so we're actually going to remove an electron, so we end up with 8 total in our structure. And now we build it just like what we've talked about previously. Attach everything to your central atom with single bonds. And you go through it, you find that all your octet rules are satisfied, so we also have 8 in our structure, so we're good. PO4 3-, again, this is another one where formal charge would be violated if we were to look at this from a more advanced chemistry perspective, but we're trying to keep it simple for this course. So phosphorus is 5, 4 oxygens is a total of 24, so that's 29, but we have a 3- charge, so we add 3 electrons to it, so it means we need 32 in our structure. And again, exact same steps we've done previously. Sorry, I'm a little low on room, and I'm using a stylus that is not optimal, to say the least, but it does showcase the point. So again, the polyatomic ion Lewis dot structure is very similar to the Lewis dot structures we've looked at previously, okay? So we're going to look at the next step of this, which is how does the structure of this determine its shape in 3-dimensional space? I'll bring that to you here in a moment.